Today I will speak about. Começar? Good. Today I will speak about Dedekind rings, which are very similar to what we had last time. In fact, discrete valuation ring is a special kind of Dedekind ring. The difference is that Dedekind ring is the kind of ring which has all local rings, discrete valuations. Well, there are several definitions which are equivalent. I can actually list them now, and during the lecture I will prove their equivalence. So first, the definition which is here. So Dedekind ring, R is Dedekind ring if all fractional ideals I in K of R are invertible. So example, if we have a principal ideal ring, well, what is written here is of course false. I'm sorry about this, but what is true principal ideal ring in which is where is the so principal ideal ring is not Dedekind because you can have, oh, sorry, yeah, principal ideal ring is Dedekind, of course. Let's prove this. So we have some ideal inside K of R. So the Dedekind ring is a ring where all fractional ideals are invertible. Well, if they are principal, they are invertible. Yeah, without the divisors, right? Yeah, but since we already have written K of R, it has no Z divisors. Thank you. Yes. So principal ideal ring is Dedekind. Take some ideal I inside K of R. Since it's fractional ideal, we have AI is an R, but this means that AI is since this is an ideal there, and its submodel is an ideal, and any ideal is principal because it's principal ideal ring, then this is equal to B, and then I is generated by B divided by A. This submodel in K of R, which is generated by A of B, is principal. It's what is called cyclic or principal. What is important that it is invertible because what is invertible? It's something which we discussed last time. Invertible is the same as projective. In particular, all three models are invertible. So this is free. It's freely generated by B by A. Then it is invertible, and these two models are isomorphic. I and AI, I and B are isomorphic. So they're all invertible. And in fact, you can invert it because I minus 1 will be just generated by A divided by B. Oh, yeah. B divided Yeah, this is B by A and this is A by B. Okay. So we have a trivial lemma. I think we had it last time, but let's repeat it. Suppose you have a prime, any ideal or ideal over a ring, not necessarily prime, but some non-zero probably ideal. Well, any ideal. So you have P and R ideal. And suppose that it is free. P is free as our model. Then P is principal. Okay, so proof. So P is direct sum of EI R times R. So these are generators of your ideal, and they can't intersect. EI R intersected with EJ R is 0. And this means that EI EJ is 0. But since the first component is freely generated by R, this can't happen. Well, there are no zero divisors. Well, there could be zero divisors. Generally, we assume that no zero divisors. But anyway, in that case, this is impossible because this model, EI times R, is freely generated by EI. So this can't, the product can't be zero because it's non-zero in R, because if you think of EI as a generator, this is just equal to generated times EJ. Can't be zero. Sorry? No assumptions. Just ideal is free as our model. This is the only assumption we need.
It's fine if you generate. You use it if it's fine. If there is fine inside.
No. Why? It's free model, so it's it could be infinite. Doesn't matter. Okay, it should be intersection. Sorry about this. Okay, so let me list you some other equivalent conditions for Dedekind rings. So our Dedekind this is in fact equivalent to R being all local rings of R being DVR, being discrete variation rings. And this is also equivalent to R being rule dimension 1, integrally closed, and Noetherian. So bit by bit I will prove all these equivalence. So let's start with the first one. So I would prove that if you have maximal ring in the Dedekind ring, that its localization is the discrete relation ring. So proposition 1. R Dedekind ring and M maximal ideal and then Rm localization. So we localize over all elements which are not in M. then Rm is discrete relation ring. And the proof is pretty elementary because it follows from this lemma. We have the maximal ideal M in Rm is invertible. Well, localization of invertible model is invertible. So if you take a ring, you localize it, you take then localization of any fractional submodel in this ring becomes invertible just because you have, what is invertibility? It's I minus 1 is equal to R. Well, you localize this, remains true. What you need is you need to express unit in R through this product, and then after localization, this I becomes localization of I minus 1 becomes localization of I minus 1, and the product becomes a product. So you have this maximal ideal in Rm, but since it's invertible, this is something we had on the past lecture, this implies that M is projective. In fact, invertibility of a model is equivalent to being projective, and this in turn implies, because M, well, M is projective finally generated. Then this implies that M is free, something that we had last time. And this implies that by this lemma that M is maximal, is principal. Okay, and there was this characterization of Dedekind rings, which are, of discrete relation ring, which are rings with maximal ideal principal. So it's local rings with principal maximal ideal. So then Rn is dvr. So you just have the nu of x is equal to infinitum from so minimum for all n, such that x belongs to m power n, maximum, sorry. And since m is principal, this is equivalent to x being divisible by generator of, well, you just decompose x as a product of this generator of maximal ideal, p power n times invertible. So this evaluation is in fact pair evaluation. So it is this something we had last time. So a ring with maximal ideal, local ring with maximal ideal. Principal is discrete relation ring. Okay. And now we have a corollary. Discrete relation ring has true dimension Well, if you want to check crude dimension of a ring, you take any minimal ideal and you localize it. In this minimal ideal, it's sufficient to check the crude dimension of this localization because all ideals which belong to this maximal ideal will survive under this localization. There is an embedding from ideals, for a set of ideals in localization to a set of ideals of a ring. And this embedding takes its image is all ideals which belong to the ideal you localized. So in particular, if you have chain of ideals in a ring, this would give you a chain of ideals in its localization. You just take the biggest of these ideals and embed it to a maximal ideal and localize. But since this would give you only two ideals, I mean, this discrete relation ring has only two ideals, this means that your ring you started from also has only no more than two, all chains of ideals, of prime ideals, has length no more than 2. You have 0 and you have your maximal ideal, and that's it. You don't have any ideals in between. Okay, now I'm doing something which is very basic and very fundamental in algebraic geometry. It's a lemma which sort of starts with scheme theory. So lemma. You have a ring without zero divisor. In fact, you don't care about zero divisors. I don't think you need it. Just any ring. And S set of maximal ideals. Well, you probably need no zero divisors. Well, you can avoid this condition, but let's now not avoid it. Maximal ideals, P inside R, and you have RP as localization. And you can consider RP as a subring in K of R in the fraction field. This is why we need no zero divisors to embed it somewhere in some ambient space. Then you take intersection for RP, and it will give you R.
What does the sign of intersection mean?
Sorry?
I mean, the different localization.
For all P in S.
You need them, like to make sense, you need them to sit in one space.
Yeah, in K of R.
Out.
This is why I need. In fact, you don't need it. You can, if you're clever enough, you can state it without this assumption, but it would take more work, and we don't care. But it is true generally. Okay, so proof. Okay, it's sort of clear that R belongs to this intersection. So what we need is to take some x in this intersection, prove that it is in R. We have x in intersection for all P and S, RP. Well, nobody promised to us that it will be in R, but it's definitely in K of R. So we can take ideal of all elements of R, all A inside R, such that AX belongs to R. This is an ideal, and it is non-empty because X belongs to K of R. This is well-defined ideal. Okay, it could be not ideal, it could be non-proper ideal, it could be R. But suppose it's not. If I is not equal to R, we can take P maximal, well, M maximal ideal, take M maximal ideal containing I. So I is contained in M. It exists by its own lemma. Any ideal is contained in a maximal ideal. Okay, then AX belongs to R for some A not an M. For some A not in M. This is because X belongs to Rm. X belongs to Rm, and this means that X is obtained from some element of R by multiplication by some A which is not in M, by definition. But this is a contradiction, because this implies that A doesn't belong to M, but A belongs to I. Can't be, because I sits in M. So this is impossible. On the scheme language, this means that we have a section of the sheaf of regular functions. It is given by a global regular functions. So the presheaf of regular functions is indeed a sheaf. But if you don't scheme language, you don't care. Okay, so now I can prove the theorem that every Dedekind ring is Noetherian and integrally closed. So this is what is written. Yeah, here. You don't. It will be crude dimension 1 a posteriori. So, theorem. R is Dedekind. Then R is Noetherian plus integrally so proof. Well, step 1 is elementary. This is Noetherianity. The point is that invertible ideals are projective finitely generated. So all ideals are, well, projective, and what is important, finitely generated, because they are invertible. This implies that R is Noetherian, because Noetherian is precisely when you have all ideals finitely generated. And here you have all ideals which are invertible models. Invertible fractional. So all ideals are fractional ideals, or all fractional ideals are invertible, and all invertible are projective. Now step 2. Suppose you have some x inside K of R. Well, I just removed the proposition I'm going to use, but I hope you remember it. And it's finite over R. This implies that X is finite over Rp for each P. It's already finite over X, so it's not a big deal. And this implies that X belongs to Rp because Rp is the where. And this implies that X belongs to an intersection of all Rp, which, as we just proved, is R. And this implies that R is integrally closed. Okay, so we prove that all the Dedekind rings are Noetherian and integrally closed. Okay? Converse is also true, but you need Noetherianity. Theorem. Any Noetherian integrally closed no, of course it should be also, this is something missing, namely I missed that it should be also Krull dimension 1. Sorry about this, this is an error, I should correct it. Ring is Dedekind. Of course, I mean, polynomial rings are not Krull dimension 1, so they are not Dedekind. Sorry. Proof. Okay, so you have I inside R, an ideal. Now you have all the prime ideals, which are all discrete valuation rings. So for each prime ideal P in non-zero in R, Rp is dvr because it's Noetherian, integrally closed, and Krull dimension 1. So local rings which have this property are discrete relation rings. And this implies that your so this integrally closed, so this is Dedekind. Yeah, something is wrong here. Let me give you the proof. So what we need is, by the previous it's an error here, I'm sorry. So our condition for Dedekind, there was, I think, only one so far, right? Then something is Dedekind. Is that we need that any model, like any model, or any, in fact, it's true for any, it suffices to prove it for any ideal. We need to prove that I minus 1 is R. But this, we know this for each local ring. So for each localization, Rp, we have I localized in P, is equal to Rp. Okay, so we take intersection of I minus 1 of rho P, and it will give us R, because this will give us intersection of Rp for rho P. And this, of course, again, this is intersection. You take a model, and any model M, any ideal M inside K of R, any fraction ideal, and you take intersection of MP for all P, for all prime P. This gives you M. The argument is the same as for the elements of, just literally the same as we did for elements of R. So it's the same. So this is R. So this gives us R, and this implies Dedekind condition. And sorry for something silly on slides. Yeah. So our definition of Dedekind ring is that a ring is Dedekind if all of all fractional ideals are invertible. In fact, you can prove it. It suffices to prove it only for ideals in R. Because what is fractional ideal? It's an ideal in R multiplied by some. So it's t minus 1 times ideal in I, right? Because every fractional ideal becomes an ideal in I if multiplied by some t, then. And of course, this multiplication by t is an isomorphism of R models. So this implies that it suffices to prove invertibility only for ideals. So we start with an ideal, and we want to prove this. We want to prove that I minus 1 is equal to R. Instead of that, we prove that intersection of I minus 1 for all P, this localization is R. And we notice that this intersection is in fact equal to I minus 1. Because intersection of localizations of any model, any fractional ideal is itself. And of course, this operation taken minus 1 and multiplication, they all are compatible with localizations, essentially by definition. So we have, and of course, so what we have is that I minus 1 localized in P is Rp. This is because our ring is Noetherian integrally closed, full dimension 1. So Rp is Noetherian. Oh, sorry. Rp is discrete relation ring. And for discrete relation ring, we know that all ideals are principal. And this implies that I minus 1 is always R. So after passing to localization, we obtain this invertibility. And then we say, OK, we have a model which is invertible for all localization, then it is invertible. This is because you take intersection of model for all localization, you obtain this model. This is the same argument. You just write an ideal. And well, this is the same argument as we had. OK. And let me give an example. example. This is the, actually this was why Kummer and Dedekind were starting doing commutative algebra. It was they started doing it long before it was useful in algebraic geometry, because they wanted to do number theory. So suppose you have K finite extension of Q. Finite extension. Then K is called arithmetic algebraic number field. Number field. There are also other terms like arithmetic fields, but we shall use algebraic number field. And then you take O of K, which is by definition integral closure of Z integers in K. And this is called O of K is integers in K. So algebraic integers or the ring of integers. And then what we have is that, so corollary or example, of K is Dedekind. Well, it is integrally closed, Noetherian, full dimensional. So it's it has full dimension 1 because Z has full dimension 1, and any finite extension doesn't change full dimension. This is what we had when we proved this going up and going down theorem of Cohen and Zeidenberg. So Cohen and Zeidenberg implied that finite extension doesn't change full dimension. And since full dimension of Z is 1, full dimension of this ring of integers is also 1. So we have Noetherian integrally closed, full dimension 1 ring. It's integrally closed by definition. We're taking trivial closure. So it is Dedekind. Am I clear? Okay. Now there's one more characterization of Dedekind rings. So you have a ring without zero divisors and not a field. So there are no zero divisors and not a field. Then the following are equivalent. First, R is Dedekind. Second, R is Noetherian. And localization, each localization in prime ideal is discrete relation link. And the final statement is every ideal of R is a product of maximal ideals. So product we understand in the standard way. You just take product of, if you have two ideals, you take pairwise product from the first and from the second ideal and generate an ideal by these products. Okay, so proof. So 1 implies 2 by preposition 1. This is where we started from. We said that, okay, you have a local ring which has maximal ideal invertible, then this maximal ideal is actually free, and free means that it is principal. Okay. So 2 implies 1. This is something we discussed already. This is because R is intersection of R of localizations. They are all DVR, so they are integrally closed. And intersection of this integrally closed is integrally closed. So RP DVR, very integrally closed. And then R is intersection of RP also. Okay, so these two are equivalent. It remains to prove this product decomposition. This was actually the reason for the word ideal, because Kummer, who invented the word, wanted to have ideal numbers. In fact, you will see today that the prime decomposition in that sense of ideal numbers is in fact unique. So this, you should think about this decomposition as prime decomposition. So this was step 1. Step 2. We take an ideal. I want to decompose every ideal. So I have an ideal inside R. If I is maximal, we are done. There's nothing to prove. So we suppose that I non-maximal. Then there's maximal ideal strictly containing I. Okay, so what we have now is that m minus 1 is R. Well, what is important now is not that it is R, but that it is contained in R. Because this implies that I m minus 1 is also contained in R. It's a strictly bigger ideal, because I m minus 1 m is equal to I. Here I use this equality, in fact. And then I m minus 1 it strictly contains I. Well, multiplication by m minus 1 by m increases, and by m minus 1 strictly decreases the ideal. multiplication by m strictly increases, so multiplication by m minus 1 strictly decreases because of this condition. Okay, so we can repeat this procedure until we arrive at the maximal ideal, or maybe indefinitely, but indefinitely it's impossible because it's Noetherian. So you have I, it belongs to m1 minus 1I, it belongs to m1 minus 1, m2 minus 1I, and so on. And all these things are strict for that reason. So this is a strict inclusion. Because this strict inclusion, because I strictly included in mi, and this is strict because Nakayama lemma. Multiplication by maximal ideal always decreases something by Nakayama. Okay, this is because intersection of many copies of m is 0. So if I is equal to mi, this means that mi is 0, which now doesn't happen. So. Okay, so you have m. Yeah, it's opposite inclusion. You have this ideal is bigger than that. No, yeah, this is small. This is smaller. This is smaller than that. This is smaller than that, and so on. Yeah, you have increasing sequence of ideals, which has to stabilize by Noetherianity. So in the end, we obtain a maximal ideal. We obtain that m1 minus 1, m2 minus 2, and so on, mn minus n times I is equal to m, so a maximal ideal. Make clear? So again, suppose that m belongs to, I is contained in m. Then you can take I m minus 1, it will be also an ideal, which will be strictly smaller than I m minus 1. You can increase. And you do it until you arrive at a maximal ideal. This has to stabilize. So at some point, this procedure cannot continue, and it would stop. And this means now I multiply this by m1 minus 1, m2 minus 2, and so on. Our ideal is invertible, so it makes sense. It is equal to m times product of mi. I just multiply everything by this product, both sides. Okay, it's a product of maximal ideals. We're done. Yeah, it stabilizes because it's Noetherian. This is why we have to assume it is Noetherian. It won't work otherwise.
There's something strange with inclusion. So if you have an ideal, then it's a subset, a proper subset
of this ideal. And this is proper subset of that ideal, and so on. So in each step, I start with an ideal m, I put it into a maximal ideal, and I invert this maximal ideal. So if you invert bigger ideals,
so just can like multiply this line
yeah. I just take this inclusion and I multiply both sides by m minus 1. And I use the invertibility of m. So this inclusion is strict because if we multiply it by m, we obtain I strictly included in m. And this is strict inclusion by our assumptions. Okay, we decomposed an ideal into a product of prime ideals or maximal ideals. Okay, so let's do converse. Converses are entirely trivial because, yeah, so you have a localization so it's step 3 now. So I use the I obtain 2 from 3. I use the decomposition of an ideal onto product to obtain that every local ring is divar. So have P is a maximal ideal. RP for each I inside the RP. So for each I inside RP, we have I is a product of maximal ideals. To note why this is so, this is again for the reason which we had, I think it was in lecture 3, that after passing to localization, you so all ideals of localization correspond to ideals in your ring. There's an injective map from ideals in localization to ideals in your ring. In particular, if you have an ideal in this RP, it gives you an ideal in R. And this is ideal is a product of ideals. So this, it gives you a decomposition for the corresponding ideals. But then the maximal ideals of RP is just P. There's no other. So this means that I is P power n. Well, maximal ideal power n. And this is something we had already. So this means that our RP is actually principal ideal. Because you can apply this to the, you take any element of maximal ideal, it would generate maximal ideal because if you take x inside M without M square, X would generate a maximal ideal. It can generate M square and so on. So it has to generate maximal ideal, then maximal ideal is principal, and we are running the same machine as we did already several times today, obtaining a discrete relation ring. So if you have a local ring with all ideals which are power of maximal ideal, then it is actually principal ideal ring and it is discrete relation ring. So this prime ideal decomposition immediately implies that any local rings of your ring are actually are discrete relation rings. Should I repeat? So you start with, you take some I in RP, you take its intersection with R. This intersection is a product of prime ideals. Then you localize these prime ideals, and you obtain localization of a prime ideal is either R or a prime ideal. So you obtain a prime ideal in RP, maximal ideal even, in RP, which several copies of it multiplied give you I. Okay, should I go on? Any questions? Clear? I can repeat. Should I? Step 2 or step 3? Yeah, so now we want to prove that if you have a ring with prime decomposition, then with this property, then every localization of this ring also has this property. Because if your local ring has this property and has, then it is clearly DVR. This is what we had in the first lemma in the first slide. So to obtain, to prove this, to obtain this conclusion, we need to prove that our local ring RP has a prime decomposition of ideals. Okay, so you have RP, an ideal I in it, IP, and you take IP intersected with R, which gives you an ideal I. Now you know that I is a product of prime ideals or maximal ideals, and you localize them. You have IP is product of localizations of PI. So now what can happen with that localization? First, if you localize so I claim that PI localized in P is either RP or prime ideal. Either that or this. So suppose it's clearly an RP model. It's an RP submodel in RP. So it is either all RP or ideal. And why it is prime? This is because if you have x, y in RP such that x, y belongs to PI localized in P, then you can multiply x, y, multiply them by some alpha. Alpha not is not, it's invertible, so it's not in P. It's the guys you should do to localize. Then you have x alpha, well, alpha 1, alpha 2. X alpha belongs to R, x alpha 1. Y alpha 2 belongs to R, and you have x alpha 1, y alpha 2 in P1, where each of them is not, yeah. Now, so if so what can happen with prime ideal after you localize? If it is not contained in P, it will be just, it will become 1. So it's not an interesting case. Interesting case is also if P1 is equal to P. And in that case, this would contradict this ideal being prime. So this means that it will, this ideal will become RP or it will be prime after localization. So this depends on whether you have any elements in P1 but don't belong to P. If there are elements in P1 which don't belong to P, after localization, this just this becomes R. Because you obtained unity from by taking some element from here and inverting it. So it becomes RP. But if it doesn't have any elements which don't belong to P, this means that Pi is inside P. In our case, that just means that they coincide because there's just one prime ideal, but it doesn't really matter. In that case, this would contribute to this prime decomposition. And it is prime. What I told you just means that prime decomposition is compatible with localizations, which is intuitively clear, I think. Just localization somehow, it makes some ideals, it makes them into RP. But it still is compatible with its multiplicative operator on, yeah, it's probably possible to say like that. You have some, yeah, you don't need anything about prime. You just, if you have I is equal to I1 dot IN, this is your decomposition. Then after localization, you obtain localized is equal to product of IJ localized, right? This is your decomposition. Now look, you don't have that many. So localization of a prime ideal is prime, and you don't have that many prime ideals in your ring because it's Krull dimension. Well, doesn't matter. So what is important is localization of prime as prime. So this gives you a prime decomposition in the local ring. And to check that localization of prime is prime, you just take, you use what is written there. You have X inside RP without this localization, IP, Y inside RP without this localization, IP. You take XY, and you suppose that it belongs to IP. Then you multiply XY by some denominators, obtaining X alpha 1, Y alpha 2 belongs to I. And since I prime, this implies that X alpha 1, X alpha 1 and alpha 2, they sit outside the invertible. So X and Y belong to P, belong to I. So if you localize prime ideal, it remains prime. Now this is very basic actually, that if localization of prime ideals is prime, this is something we discussed a lot, I think. So there is not, shouldn't be difficult to, should I go on? Or may we have questions? Okay, let's have a break. 10 interval, 5 minutes. Yeah. So I would now list some properties of the Dedekind rings. So first, the first observation is that something that always a stumbling block when you, so you have some principal ideals rings and you have some factorial rings, and this is both directions are not, implications are not true. So you might have guys which are factorial but not principal ideals, like rings of polynomials. But for Dedekind rings, it's not so. So Dedekind ring is factorial. It's not always factorial, obviously, because this is something that people know, that there are rings of algebraic integers which are not like factorial. Something that people knew even in early 19th century. But factoriality is the principal ideals. So theory R Dedekind ring is factorial if and only if R is principal ideal ring. So proof. Okay, to obtain factoriality from principal ideal, what you need is only to have the irreducible decomposition. But it's Dedekind, so it's Noetherian. And this means that if you try to decompose a number, you decompose it. This gives you, like you have x is equal to p1 x1. The ideal generated by x1 is bigger than ideal generated by x. Strictly bigger if p1 is not invertible. This is equal to p1, p2, x2, and so on. So you have a chain of ideals which has to stop unless, because it's Noetherian, so you have you have a reducible decomposition. And now, if you have two ideals which are both principal, their intersection is lowest, well, the sum is lowest common denominator, and the intersection is, so you can have the factoriality follows from principal ideals, the same argument as for reals. You just have, if you have ideal A, you have ideal B, you have A intersected with B is A times B divided by greatest common denominator, and so on. So this gives you a standard way, the prime decomposition. So conversely, suppose it's factorial. Factoriality doesn't apply principal ideals even in the simple case such as, so this implies factoriality from principal ideals. Now suppose it's so principal ideals imply factoriality. Suppose it's factorial. Step 2. Suppose R is factorial. Now we need this ideal decomposition. Or yeah, so if factorial, then any ideal is principal, yeah. So you have suppose I have an ideal P, prime ideal. Yeah, but I start with prime. No, I want to prove that any ideal is principal. Of course, not any ideal is prime. Yeah, I start with prime ideal. And P, it contains A. And A is written as product of primes. Well, A is non-zero. And one of these primes belongs to P. Pi belongs to P. Because it's product, and P is prime. So it has to. Then you have two prime ideals, Pi, which is contained in P, right? And this and 0 is contained in the P prime. This is impossible unless they are equal, because we have rule dimension 1. It's a Dedekind thing, right? So they're equal, actually. These two ideals are equal, and this means that all prime ideals are principal, or maximal ideals. Doesn't matter because it's rule dimension 1. And now we'll gain everything because every ideal is a product of prime ideals. Prime ideals are principal, so every ideal is principal ideal. So you have a prime decomposition for free. Sorry, you have every ideal is product of prime ideals. Prime are principal, so every ideals are principal. So you have principal ideal for free. Sorry. Am I clear? Should I go on? Good. Now we have this very beautiful notion of Chinese remainder theorem, which is very basic. In fact, it's typically people do it in high school, especially when they prepare for Olympiads. But we need it in bigger generality than usual. And we need it in the biggest generality because you will see in the next slide how it is used. So let me give a definition. It's analog of coprime numbers. So you have ideals P1, P2 are coprime, or comaximal. If P1 plus P2 is equal 1. And you have several ideas. You say that I'm pairwise coprime if it's 2 for every 2 pairs. For every 2 ideals in this set. This is ideals. Non-propositional. And its proof will take us pretty much everything because it takes work. Okay, so I have comaximal ideals P1 dot Pn inside R are pairwise comaximal. This means that for every pair of these ideals, you have this property. Then, intersection of these ideals is their product. And second, the natural map, moreover, you have a natural map chi from R quotient by product or intersection of Pi mapped. Well, here it is intersection, so let's write intersection. Mapped to direct sum of R quotient Pi. Just you take, since it's by intersection, this ideal contains Pi, and you can take a sequence of such maps and take the direct sum. Is an isomorphism. No. It's injective by this. By this. It's subjective. Well, it's injective for free and surjective by a complicated argument. Okay, so the first step is to prove it when we have only two ideals. It's slightly simpler. So I would prove it. Step one is a proof for two ideals. So I have P1, P2, coprime or comaximal, and yeah, n equal 2. So let's first prove the first assertion. So have x inside P1 intersected with P2, and then you have 1 is equal to P1, P2, plus P2. Then you have x is equal to x belongs to ideal generated by x times P1 plus P2. Now x belongs to P1 and P2. So this belongs to P2 times P1. So for the first step, I interpret x as an element in P2. And then I add x interpreted as an element of P1, P1 times P2. And this is, of course, equal to P1 plus P2 times P2. So you obtain this inclusion. Clear? So the idea, you can write it more. You have some elements in P1 and elements in the P2 such that x times this element is x. And then this first element is in P1, x in P2, so the product is P2 to P1. Second element is P2, the x is in P1, so the product belongs to P1, P2. But I think this notation is more clear, in fact. Okay, so this was the first assertion. Let's do the second. It is quite similar. So we have now 1 is equal to P1 plus P2, where P1 is now it's small p. P1 is an element in P1, P2 is an element in P2. And this implies that P1, or 1 minus P1, belongs to P2. This is big, this is small. And 1 minus P2 belongs to P1. And now we want to, now we can apply chi to this element. So chi to 1 minus P1 is equal to 1, 0. Because it's 1 modulo P1 and belongs to P2. And chi applied to 1 minus P2 is 0, 1. These two guys multiplicatively generate this direct sum. So they really, this implies surjectivity, but let me write it more explicitly. Because it takes some work. Well, you can see it immediately, but it's still better to write explicitly. So you have R quotient by P1 plus R quotient by P2. You have A and B here. So these are classes, and A belongs to R, B belongs to R, representatives. Now we will apply chi to A multiplied by 1 minus P1 plus B multiplied by 1 minus P2. And by this argument, we know that chi of A multiplied by 1 minus P1 is A underline 0. And chi applied to B1 minus P2 is 0, B underline. Right? Okay, add them up. You'll obtain an element of R which goes to this pair. Am I clear? Okay, so let's do that for many ideals. We use induction. So we assume that this Chinese remainder theorem is true for n minus 1. So step 2. Assume CRT when for n for n minus 1. So this implies that product from I equal n to n minus 1 of pi is equal to intersection of from I equal 1 to n minus 1 pi. And the same with the R quotient by their intersection, I equal 1 to n minus 1 pi is direct sum, again from I equal 1 to n minus 1, R quotient by pi. This is our assumption. And we want to do that for next, for n. So to see the first, we will apply, we'll notice that 1 is equal to product of Pn plus Pi, where I is equal from, it goes from 1 to n minus 1. This is because these two guys are co-prime and we apply step 1. This 1 belongs to this sum. Well, it's not step 1, it's direct. But then we open brackets and we obtain that this would give you things which, after you open the brackets, this would yeah, so this would give you like products of several copies. So after you like open the brackets and you take sums, this would give you products or intersections of one belongs to, well, sometimes you have, there are situations where you can take smaller number of terms. And there is just one way you can take all terms only once. So it will be, one would belong to a product of, so it's Pn is, can occur once to 2 times, n times, and so on. The important thing that if there are some terms which occur more than once, this, I mean, there will be a sum, and the sum will give you 1. So this, after you open the brackets and you apply the standard intersections and sums, I mean, every time you have a sum of two things which, well, it will give you pi from I equal 1 to n minus 1 plus Pn. Because otherwise you have Pn entered in there, and it is divisible to Pn, so you can put it there. Repeat. Okay, so when you open the brackets, you'll obtain things like product of sum, not all of them, of pi. Pi, so it will be like pi1, pi2, and so on, pin, and then p. This already belongs to Pn, sorry. This already belongs to Pn. So you can put it there. And then you have product of all of them without Pn. This gives you this. Okay. But this is intersection. So one belongs to intersection of all pi from I equal 1 to n plus Pn. Good. And this implies that these two ideals are comaximal. So the intersection is their product by step 1. So intersection of pi from I equal 1 to n minus 1, we intersected with Pn, is the same as product, of this Pn multiplied by intersection of n minus 1 to I equal 1 pi. And this is the same as Pn multiplied by a product from I equal 1 to n pi. So intersection is equal to the product. Good. This is the first half. The second half is very similar. So it's step 3. We have P let's write it here. We take P quotient R quotient by Pn intersected with intersection from I equal 1 to n minus 1 pi. These are two comaximal ideals. So this is the same as P quotient by Pn, direct sum, with P quotient by product from equal 1 to n minus 1 pi. Or intersection, doesn't matter, it's the same. And this, by induction assumption, this is already direct sum. So this will give you P by P, R by Pn, direct sum with big direct sum from I equal 1 to n minus 1, R quotient by Pi. We proved Chinese remainder theorem. Is it clear? Should I repeat? So it looks a bit like street magic, but it's very straightforward, in fact. This may be slightly take some work to figure out. But after you have written that, you immediately obtain this, and you are done. And this is entirely straightforward, because these two guys are co-prime, so you have this direct sum, and then you decompose this into a direct sum using the Chinese remainder. Go on? Questions? Comments? Okay, good. So this has two funny applications. The first observation is that in general, in rings, you can't have these statements like if the ring has dimension that and this, then every ideal is generated by that number of elements. This never happens. But here you have So in every Dedekind ring, every ideal is generated by two elements. So theorem, we have I inside R Dedekind, and I is non-zero ideal. And I ideal. Then R by I is principal. Ideal ring. This is actually equivalent to what is written there. In other words, for each J containing I, J is obtained by adding one element. So let me rewrite it. That is for any ideal J containing I, J is obtained from I by adding B, some element B in R. And this is the first. Moreover, I is generated by two elements. Of R. So if you have factoriality, then it's generated by one element, but even in the worst case, it's two is enough. So proof, step one. So you have I is decomposed into a product of prime ideals. I is R, well, sorry, it's P1 power K power I1, dot P n power IN. And these guys are pairwise comaximal. Pi pairwise comaximal. Because if you have a prime ideal, and it's maximal ideal as well, and you add any other element to this maximal ideal, you obtain everything. Because this maximal ideal is not contained in anything else. So adding one more element gives you one. This is why they're comaximal. But not only. Even more interesting that actually, since Pi power k, root of radical of that is pi, it can't happen that pi belongs, power k belongs to pj power l. This can't happen because you take so the ideals pi power and pi power j, p1 power j power I1 and p2 power I2 are co-prime or co-maximal. So this is because you add them together. Because the sum p1 power I1 plus p2 power I2, the radical of that is equal to p1 or just r, because it contains this, and also it's equal to p2 or r, because it contains that. P2 is different from P1, so it has to be R. This is why they are coprime. It's something we had last time, that if you have a ring of full dimension 1, then you have maximal ideal. It's, well, radical of any ideal is one of the maximal ideals. Okay. Then we have Chinese remainder theorem. Step 2, which tells us that R quotient by I is direct sum R quotient by P power Pi power Pj power Ij. Chinese remainder, right? Co-prime or co-maximal. Then you have this direct sum decomposition, but each of these quotients, in fact, the quotient of discrete relation ring. And the discrete relation ring is already principal ideal. So this is direct sum of principal ideal rings, and it is principal ideal. So if you have some element, some ideal there, is generated by something in each of these components, and you just sum these generators and obtain an ideal there. So J quotient by I is principal in R quotient by I. So this is a principal ideal ring, and also it's generated. So this means that J quotient by I is generated by B, and this means that J is generated by I plus B. Okay, so this was the first assertion. And the second assertion is simple. So we want to prove that I is generated by two elements. We already have A inside I. There is something non-zero. So you have I it contains the ideal generated by A. And you apply this theorem to this pair. So now A become I, and I become J. So this implies that I is A plus B. Okay, I'm almost done. Is it clear so far? Do you have any questions, comments? I can do more slowly. We have only one slide and a few minutes. Should go on? Good. The last slide. Uniqueness. So this is the main. I mean, it's sort of now it's almost never used. But for the guys who invented ideals, this was like groundbreaking because they thought they repaired the non-uniqueness of prime decomposition. Because, well, this is ideal numbers, and ideal numbers can be used to have uniqueness of prime decomposition in a nice way. But it's still quite useful for many purposes. Things like key theorem uses that a lot. So theorem, you have R Dedekind, you have I ideal, and it's have prime decomposition. Alpha I, prime decomposition. So Pi are prime ideals. Then it is unique. This is unique up to renumbering. Up to renumbering. It's the same as the usual prime decomposition, except that now we have the ideals and not numbers. There are no prime numbers, but there is prime decomposition for ideals. Okay, so proof. Okay, suppose we have another decomposition. So we have I is equal to product of P I power alpha I. And this product should be not alpha by beta. It's a product of P Qi, Qj, beta j. This is entirely unrelated numbers. Okay, there could be, it's possible that we have some ideals in common. So we just multiply by these ideals, and so if Qi is equal to P is equal to Pj, we take I P minus 1, and it will be a smaller decomposition. And we'll do that, we'll repeat that until there are no common factors. So we can assume that it's sufficient to prove this statement when Q and P are entirely disjoint. Suffice to prove when Pi, Qi are distinct. Pi, Qj are different, all different. Good. But then something which we already had, that if you have pairwise mutually pairwise comaximal family of ideals, then their products are also comaximal. So we had, when we proved Chinese remainder theorem, we actually proved that. This implies that product of Pi alpha I co-prime or comutual, co-maximal with product of Qj beta j. For instance, you can just take the quotients, well, it's the same argument as we did. And this implies that you have I, its intersection of this with that, but then the intersection of two coprime ideals is their product. So this I is equal to I squared. And with this impossible by Nakayama, by Elbach rule, cannot happen by rule. Okay, I'm done. This was uniqueness of decomposition. Which says that I inside intersection of all powers of I is 0. It's true in a Noetherian ring, and we are in the Dedekind, which is Noetherian, for free. Yeah, and so thanks. So there was people who asked about exam. I think we should create something like Google Doc and let people sign up for the time it's good for them, because I would just distribute some problem sets to everybody, and you would supposed to solve them and meet me when you solve them, and just explain me orally the solutions. People who are not from IMPA are not supposed to take exams at all. Yeah, that's it, right? Do you need to tell anything else? There was people who asked something.
Yeah.
This is it.
Just about exam, there was the form of the exam, the date of the exam.
Yeah, there won't be data. I will just distribute problem sets, and we shall set up with everybody who wants to pass exam convenient date. Okay. Good. Muito obrigado.